Good morning students, welcome to our online video class of chemistry. In previous section we had discussed about the difference between orbit and orbitals and also about four sets of quantum numbers. In this video we will discuss about Schrödinger wave equation and rules for filling of electrons in an orbit. Now we are going to discuss about the topic quantum mechanical model of atom. Macroscopic objects have particle character, so their motion can be described on the basis of Newton's law of motion. But early 20th century, scientists found that classical mechanics could not correctly interpret the behavior of extremely small particles, that is microscopic objects such as electrons, protons and neutrons. Such microscopic objects have both the wave-like and particle-like behavior. It cannot be described by classical mechanics. In order to describe both wave-like and particle-like behavior of microscopic objects, a new branch of science was developed, that is quantum mechanics. And it was developed independently by Werner Heisenberg and Erwin Schrödinger in 1926. And the Schrödinger described the wave motion of electron in three-dimensional space around the nucleus by mathematical equation known as Schrödinger wave equation. That is dou square psi by dou h square plus dou square psi by dou y square plus dou square psi by dou z square plus each pi square m by h square into e minus v into psi equals 0. Where dou square is the second derivative with respect to h, y, z and psi is the Schrödinger wave function. E is the energy and V is the potential. In short, the wave equation may be written as h psi equal to E psi, where h is the Hamiltonian operator, energy operator, and E is the energy eigenvalue. The wave function psi is a solution of Schrödinger equation, and it describes the behavior of electron in a region of space called the atomic orbital. We can find energy values that are associated with a particular wave function. Significance of psi wave function is psi is amplitude of the electron wave. Psi has no physical significance, but its square has physical significance. Psi square, that is square of wave function, gives the intensity of the electron at any point. Psi square gives the probability of finding an electron in a given region around the nucleus, and psi square is termed as probability density and psi is called probability amplitude. Now we are going to discuss about shapes of the atomic orbitals. Observe the figure. The figure shows the variation of psi and psi square with r for 1s and 2s orbital. For 1s orbital, the probability density is maximum at the nucleus and it decreases sharply as we move away from it. And for 2s orbital, the probability density first decreases sharply to 0 and then again starts increasing. The region where the probability density function reduced to 0 is called a nodal surface or node. For ns orbital, there are n-1 nodes. For 2s orbital, there is 1 node. And for 2s orbital, there are 2 nodes. For 2s orbital, n-1 node, that means 2 minus 1, that is 1 node. And for 3s orbital, n-1 equal 3 minus 1, which is equal 2 nodes. For s orbital, L azimuthal quantum number is 0. Hence, the magnetic quantum number m can have only one value, that is 0. That means the probability of finding the electron in s orbital is same in all directions. S orbital hence has spherical symmetry. In the case of 2s orbital, there is a spherical shell where the electron density is 0. That is called a node. What is node? Node is the point at which electron density is 0. This is the node of 2s atomic orbital. And p orbital. For p orbitals, L equals 1. Azimuthal quantum number L equal 1. And hence m can have 3 values. That is plus 1, 0, minus 1. That means there are 3 p orbitals in each p subshells. These are the 3 p orbitals are px, py and pz. And each p orbital has dumbbell shape. P orbitals are dumbbell shape and there are 3 p orbitals, that are px, py and pz. And d orbital for L equal 2. Hence m can have 5 values, that are plus 2, plus 1, 0, negative 1, negative 2. That means there are 5 d orbitals in each d subshells, that are dxy, dxz, dyz, dx square minus y square and dz square. 5 d orbitals are dxy, dxz, dyz, dx square minus y square and dz square. The shape of the first 4 d orbitals are double dumbbell shape, and that of fifth dz square orbital is shaped like a single dumbbell shape along the z axis with a donut-like ring around the nucleus on the xy plane. Hence, it is also called donut-shaped orbital. The energies of the orbital. The energy of an orbital in a hydrogen atom is determined only by the principal quantum number. Thus, the energy of orbital in hydrogen atom increases as follows. That is, 1s is less than 2s equal to p, which is less than 3s, which is equal 3p and 3d, which is less than 4, which is equals 4p, 4d and 4f. Orbitals have the same energy are called degenerate energy level. The energy of an electron in a multiple electron atom depends upon its principal quantum number and azimuthal quantum number. It depends upon both the main energy shell and subshell. Lower the value of n plus 1 for an orbital, lower its energy. When two orbitals have same value of n plus 1, the orbital with a lower value of n will have lower energy. Next topic is rules for filling of electrons in various orbitals. The filling of electrons into the orbital of different atoms take place according to 3 rules, that are Aufbau principle, Pauli's exclusion principle and Hund's rule of maximum multiplicity. German word Aufbau means build up. The building up of orbitals means the filling up of orbital with the electrons. And the principle states that orbitals are filled in the order of their increasing energies. That is, electrons first occupy the lowest energy orbital and then to the highest energy orbital. And the increasing order of energy of atomic orbitals are 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d and 7p. Therefore, first the electron filled in the lowest atomic orbital, that is 1s, then 2s, 2p, 3s, 3p, 4s on. We have seen the increasing order of energy of atomic orbital. 1s, 2s, 2p, 3s, 3p, 4s and 3d and so on. Why 4s comes before 3d? The reason for that, orbitals are filled in the order of increasing value of n plus l value. N is principal quantum number, L is azimuthal quantum number. So for example 4s, n plus l value equal 4 plus 0 which is equal 4 is filled before 3d, because n plus l value of 3d is 3 plus 2 which is equal 5. If two orbitals have same n plus l value, the one with the lower n value will be filled first. For example 2p, n plus l value equal 3 and is filled before 3s. N plus l value of 3s is also 3, but 2p has lower value of n, so 2p filled first. This is Pauli's exclusion principle. It states that no two electrons in an atom can have the same set of 4 quantum numbers. And it is also stated that only two electrons may exist in the same orbital, and those electrons must have opposite spin. For example, if there is two electrons in an orbital have same value for n, l and m, they should have different value for s. That is, if s equal plus half for the first electron, it should be negative half for the second electron. Therefore, from this principle we can conclude that an orbital can have maximum of 2 electrons and they must have opposite spin. For example, S subshell can have a maximum of 2 electrons because there is only one orbital is for S subshell. And for P subshell, the maximum number of electrons which can accommodate is 6 electrons. And the P subshell contain 3 orbital. D subshell can have maximum of 10 electrons because D subshell contain 5 orbital. And the F subshell can have maximum of 14 electrons. F subshell contain 7 orbitals. Hund's rule of maximum multiplicity. According to this rule, electron pairing will not take place in orbitals of same energy or same subshell until each orbital is singly filled. For example, the 6 electrons in carbon atom are distributed as 1s2, 2s2, 2px1, 2py1, not as 1s2, 2s2, 2px2. This is the correct form of filling of electrons. It is incorrect. That is Hund's rule of maximum multiplicity.